Hello, welcome again. We continue with our discussions and we will introduce continuous probability distribution, but we will be discussing one important continuous probability distribution, that is the normal distribution. This is in two parts. So we'll take the first part. As you know, we discussed earlier probability distribution, but those were discrete distributions. The continuous random variable, as we indicated, is one that can assume an infinite number of possible values within a specified range. So, as I indicated, we will look at the normal distribution. Now, it is expected at the end of the session, you will be able to list the characteristics of the normal distribution, define and calculate what is called the z-values, and then you be able to calculate the probability that a random variable lies between 2 points using what is called the standard normal distribution. The session is outlined as follows. We'll start first by looking at probability distributions in the continuous sense, and then talk about the normal distribution, the importance of the normal distribution, and then illustrate how we can calculate probabilities using the standard normal. As usual, these are your reference texts, Michael Barrow, and then Mason, Lind, and Marshall. Let's begin by looking at probability distributions for continuous random variables. Now, you recall that in discussing frequency distributions, we said that when you have a frequency distribution, you can use it to draw a histogram. Now, what we are saying is that when you have data on some measurements, you can characterize that data graphically, like using a histogram. So let's assume that a fast food chain producing hamburgers collects data on the weight, of 8 hamburgers measured in kilograms. Now you realize that the chef in the kitchen is going to cut it according to the size required, but sometimes it could be less or more. So when you measure, or let's say a sample of 100 hamburgers, you might not get the same size even though they are priced the same. And it is possible for us to put this in a frequency distribution and then end up drawing the histogram associated with that. So let's say that we collected data and then did a frequency distribution and then graphed it in the form of a histogram. Now you can see we have data on the weights of hamburgers, and then we constructed a frequency distribution which we have put in the form of a histogram. Now you see we've marked 0.25 here, which means 0.25 kilograms, meaning that we expect the average weight to be 0.25 kilograms. But because of some variability, some might be slightly less than 0.25, others might be slightly heavier than 0.25, but we expect the bulk to be around 0.25. That's why we have the highest bar centered on 0.25. Okay, so let's say we've drawn this histogram. You could do this for a sample size of 30 or 50. What if we decide to increase the sample size? When we raise the number of hamburgers we are weighing from, let's say, a sample of 50 to 1,000, it means that we are able to increase the number of classes, and make the classes narrower. And when we do that, it means that the number of bars we will get will be more numerous than before. So let's say we decide to make the class intervals smaller. It will allow us to get more class intervals because we've increased the number of observations. Now, when we draw the histogram, it gives you a shape like this. Now, what can you see from the shape? This shape is bell-shaped because we can approximate this histogram with a smooth curve, right? So you can see a smooth curve like this, which is bell-shaped, right? And you can see that on the next slide. So that shape of the histogram has been approximated by this smooth curve. Now this smooth curve is called a probability curve or a probability density function. And the total area under this curve is equal to 1. Remember, because we have computed relative frequencies, and the sum of the relative frequencies is equal to 1. Now, this curve is very important. It is important because we can use it to determine the probability that some measurement, let's say the weight of a randomly selected hamburger, lies within a given range. Okay? So, for example, since we now have this smooth curve, we can show that the weight is between 0.25 and 0.20 and 0.30. And it is simply finding the area under this curve from 0.20 to 0.30, which is the shaded area. And what it tells us is that it gives us the percentage or the proportion of the weights or the proportion of hamburgers that weigh between 0.20 and 0.30. Another way to say that it gives us the probability that the hamburger weighs between 0.20 and 0.30, and it is the shaded area. This is very important, and as I indicated, this curve is called the probability curve or the probability density function. And the total area under this curve or any probability density function is 1. And the probability that the random variable will assume a value between any 2 points, let's say from x1 to x2, is simply equal to the area under the curve from x1 to x2. So as we saw previously, if we want the probability that the weight is between 0.20 kilograms and 0.30 kilograms, it's a matter of finding the area under the curve from 0.2 to 0.3. And since we know the total area under the curve is 1, it means this area, which is the probability, will definitely be less than 1. So this is important, and we'll be using it to illustrate how we can calculate probabilities. Now note that because for continuous random variables, we calculate probabilities for the random variable assuming values within a given range, then therefore the probability that the random variable will assume a specific value or precise value is equal to 0. So we are interested in calculating probabilities over a given range for normally distributed variables or for continuous random variables. Let's now move to our topic 2 and discuss the special continuous probability distribution, which is called the normal distribution. The normal distribution has this formula. It looks quite frightening, but don't worry about it because we are concerned about only 2 key variables in this formula, which is called the mean of the distribution and its variance, which is sigma squared. Okay, so this is it. And I illustrated earlier that some processes are known to conform to the normal distribution, where since so many individual factors affect the phenomenon, and we say that IQs of children, for example, is normally distributed. The heights of men, it's normally distributed. That of women also normally distributed. And what we call the sample mean is also normally distributed. Now, the characteristics of the normal curve, which is like this, as you can see, is bell-shaped. It is symmetric, meaning that the left half is the exact mirror image of the right half. It is unimodal, so you see only one high point here. And then it extends from minus infinity to positive infinity. That is in theory. Now, what it means is that as you move further to the left here, the curve approaches the horizontal axis without touching it. And also on the right, it approaches the horizontal axis infinitely without touching it. When that happens, we say that the curve approaches the horizontal axis asymptotically. Okay, so this illustrates what we call an asymptote. It means that it gets closer and closer, but without touching it. Now, so let's take two examples. We know that the height of men is normally distributed, and research has shown that the average height of men is 174 centimeters with a variance of 92.16. Similarly, for women, the average height is 166 centimeters with a variance of 40.32. Clearly, you will see that on average men are taller than women. But then there's a lot of variability in the height of men, okay, compared to women, because this is a lower variance. It means that women are closer to each other in terms of height compared to men. And you can characterize that graphically here. So the blue is for men. So you see the average somewhere here. And because it's more spread out, it indicates the higher variance for men. But you see it's more narrower for women with the pink, which means that women have smaller variance. Now, we can calculate any area under the this curve we call the probability curve or the normal curve. For example, since the area under this curve is equal to 1, this shaded area in blue, we can determine its area. Now, so we can pose the question, for example, that what proportion of women are taller than 175 centimeters? It is simply the shaded area we're interested in, because you see that if women's height is normally distributed, given as this shape, it means that women who are 75 centimeters are at this point, right? And to the right of that means you are taller than 75 meters. So if you want to find a proportion of women who are taller than 75 centimeters, a matter of finding the area shaded blue. We'll illustrate how you can find that. Now, we have several normal distributions because there are two key variables. We say the mean, mu, and then the variance, sigma squared, or you can say the standard deviation, which is the square root of the variance. So depending on the value of the mean, as we saw earlier with this example, since the mean here is 174 or so, and the mean here is 166, it means that depending on the value of the mean, we can have several shapes of the normal curve, right? So that is what we're saying. So depending on the values of its parameters, as the mean and standard deviation, the location and shape of the normal curve can vary considerably. Now let's talk about the importance of the normal distribution. Now, so many random processes are known to conform to the normal distributions. And the normal distribution or probabilities can be used to approximate other probability distributions such as the binomial and the Poisson. And also the distribution of certain sample statistics such as the sample mean are approximately normally distributed. And this result is called the central limit theorem. So it allows us to do so many wonderful things that you see shortly. And we're saying that if any variable is normally distributed, then it is always true that 68.3% of the observations will lie within one standard deviation of the mean. In other words, when we say one standard deviation of the mean, we are saying that the standard, the mean, which is mu, you subtract one standard deviation from it, and then also add one standard deviation to it. It gives you a range, and we're saying that if a variable is normally distributed, we will observe 68.3% of the observations to lie within that range, and then 95.4% to lie within two standard deviations of the mean, and then 99.7% observations to lie within three standard deviations. 99.7% is nearly 100%, or 1, which is the area under the curve. So we don't expect a lot of variables, only a small minority, less than 1%, that will lie within three standard deviations of the mean. In terms of a graph, this is what it means. So when you take this point, this is mu minus 1 standard deviation, and this is mu plus 1. So for this area, this length, we're saying that 68.3% will lie within this range. But 95.4 will lie within this range from mu minus 2 sigma to mu plus 2 sigma. And then the virtually all, 100%, which is 99.7, will lie within 3 standard deviations, so which is mu minus 3 sigma to mu plus 3 sigma. So that's what it means. Now let's move on to look at how we can use the normal curve, or what is called the standard normal distribution, to calculate probabilities. Now, I indicated that normal curves vary in shapes and in location based on the values of mu, the mean, and sigma, the standard deviation. But it is also possible that we can construct another variable from the random variable x called the z variable. And this z variable is not often called the standard normal variable. So what we do is that subtract from each value of the random variable the mean, mu, and then divide the result by sigma. So it's an operation you are carrying out, which I'll show you in a moment. When you do that by subtracting from the value of each, or the value assumed by the random variable, its mean, and divide by the standard deviation, it allows us to express it as a deviation from the mean and measured in the units of standard deviation. Now, when you do that, you get this. So we are saying that if the a random variable, normally distributed random variable x, is this, we can subtract from each of the x's the mean and divide the result by the standard deviation. Now, this result gives us a variable called z, and we call this the standard normal variable. And we are saying that this standard normal variable will conform to any distribution irrespective of the value of mu and sigma. So it means that this standard normal distribution can represent all normally distributed variables irrespective of the value of their mean and standard deviation. And we are saying that the z, or the standard random variable, is normally distributed with a mean of 0 and a standard deviation of 1, or a variance of 1. Why would the mean be 0? Because you see, if you are constructing the z and it is x minus mu over sigma, where the x value is equal to the mean, then it will be 0, it will be mu minus mu, right? So this top will be 0. You divide by standard deviation, it gives you 0. Now, there are tables for the normal probability values, and these are based on what we call the standard normal, from which we can calculate or read probability values. So let's illustrate how this is done. Now, let's say that we consider the height of women, and we want to find how many standard deviations the height of 175 centimeters is above the mean of 166 centimeters for women. Now recall that we saw that the variance for women is 40.32. So the standard deviation must be 6.35. So to construct the z based on the height of women, a height of 175 centimeters will give us a corresponding z value of 1.42, and we obtain it as 175, which is the x, minus 166, which is the mu, divided by sigma, 6.35. It gives us 1.42. What this tells us is that the height of 175 centimeters is 1.42 standard deviations above the mean. In other words, to find 175, you must multiply the mean of 166 by 1.24 to get 175. So it is 1.42 standard deviations above the mean. Okay? So once you are able to find the z value, you can read from the table. And we can read this from the normal tables. And the normal tables are found in any standard statistics text. And I'll illustrate how it is done. Now, since we're saying that the distribution is symmetric. It's a bell shape, okay, that curve. If we know the mean, which is 166, and it is 0 for the standard normal, we want to find the area under the normal curve, which is 1 to the right of 1.42. So you can read that from the table. Now, so the z value we saw, 1.42, is represented. So you see this extreme column gives us the z values. And what you find in the middle part gives us the area or the probability value. So for 1.42, you have to look at the extreme left column, which is the z column, and find your 1.4. But it is 1.42, so you pick your 1.4, and then the remainder of the decimal places is 0.02. So it's 1.4 here and 0.02. The intersection is 0.0778. Okay? What this tells you is that the area under the normal curve to the right of 1.42 is 0.0778, or you can say 7.78%. Okay? So basically, this is what it means. And it is equivalent to asking the question that what is the probability that the height of a woman is above 175 centimeters. Now, it means that your 0.0778 or 7.78%, as you can see, which we got as our answer, simply tells us that it is only about 7.78% of women who are taller than 175 centimeters. Basically, that's it is. So another way to pose the question is to say that what is the probability, okay, that the height of a randomly chosen woman is above 175 centimeters. Now, to do that, because you cannot read for the x in the table, you convert the x to the z component. And we are saying that to convert the x, which is 175, to its equivalent z, you subtract the mean, mu, from the x and divide by the standard deviation. So what we did, as you saw earlier, is to subtract the mean, which is 166, from the 175, divide by standard deviation, gives us 1.42. So our z of 1.42, okay, corresponds to x of 175. Now, so you read for the z in the table, and this is the table. Now, this table that I'm illustrating gives us the area to the right. The area to the right. Let me illustrate that here with this curve. You saw this curve earlier, and we're saying that the table I described will give you areas to the right. Okay, so let's say point to the right of 175, say. So it means that once you have your value as 1.42, you just read for 1.4 and 0.02. Okay, it gives you your answer. But there are other normal tables. For example, there's this other table that I'm displaying. Instead of it giving you the area to the right, it gives you the area between 0, mu being 0, up to mu being a certain value z, which is in this case 1.42, right? So it tells you that the area under the curve, which is shaded, okay, from mu or z being equal to 0 to z equal to 1.45 is equal to 0.4265, right? So note that the total area under this curve is 1. So the half of it, the half to the right of 0 must be what? 0.5. And if the shaded part is 0.4265, it means the unshaded part must be 0.0735, okay? 0.0735, right? So even if you want this area, which is unshaded, to the right of 1.45, and you are using this particular table, all you do is to find the shaded area and subtract from 0.5, because the whole of the area to the right of mu equals 0 is 0.5. But we know the shaded area to be 0.4265. Assuming we're interested in the right tail here, the unshaded right tail, then all you can do is the whole of this area, which is 0.5, minus this shaded area, and we got that as 0.0735. So it means that you can use this table, and I'll illustrate. Now, earlier on, we wanted to calculate the probability that z was was greater than 1.42, and we got our answer as 0.0778, right? Now, to read from this table, because we know the total area to the right of 0 is 0.5, and this table is called the half table because it gives the area under the curve from 0 up to the end here, right? Z values. So since we know that this table gives us the area from 0, z equal to 0 to z equal 1.42 that we are interested in, we just come here and read 1.4, right? And 0.2. This. Now this gives us 0.4222. So to find to the right of 1.42, it's simply 0.5 minus 0.4222. And when you do that, as you can see, I've indicated that, right? It is 0.5 minus 0.4222, and it gives you the same answer, 0.0778, as before. So irrespective of whether you are using the first table I introduced you to or this other table called the half table, you can calculate the probabilities appropriately. Now let's move on because we don't have a lot of time. And I've solved quite a number of examples, okay? And you will see how to read it. I'll illustrate. So let's say, take another example. This question says that suppose the time required to repair equipment by company maintenance personnel is normally distributed with a mean of 50 minutes and standard deviation of 10 minutes. What is the probability that a randomly chosen equipment will require between 50 and 60 minutes to repair? So what we want to calculate, if we define X to be the equipment repair time, then we want to find the probability that the equipment repair time lies between 50 and 60 minutes. So we'll just write it simply as probability that X lies between 50 and 60. Now, but we're saying that we should convert to each Z component. And with the Z, you need the mean, which is mu, 50, and sigma, standard deviation, which is 10. So we just move here. When X is 50, its corresponding Z value is 0. And when X is 60, its corresponding Z value is 1. So the problem which says that probability of X between 50 and 60 reduces to the probability of Z lying between 0 and 1. And then you read from the table, because we're saying that this table, our half table, gives the probability from 0, which is the lower bound, to an upper bound. So in our previous, in this example, the lower bound is given, which is 0. So all you need to do is to read for the upper bound of 1. So how do you read? 1 is the same as 1.000, right? So you just come here and read 1.0 and 00. So that's the intersection here. What do you see there? It is 0.3413, right? So the probability that the equipment repair time is between 50 and 60 minutes is 0.3413. It's as simple as that. Okay? Now, there are other examples that I've solved. For example, we want to find the probability that the more than 70 minutes will be required to repair the equipment. And I have solved it following the procedures. You see it. We also have another which says that we want to find the probability that the equipment repair time is between 35 and 50 minutes. Now, when you convert this to EZ component, it is now probability that z lies between minus 1.5 and 0, because the z value corresponding to an x value of 35 is minus 1.5. But the probability that it lies between minus 1.5 and 0 is the same as it lying between 0 and 1.5, because the curve is symmetrical. So all you have to do is to read in the half table for 1.5 under 0, 0, and it gives you 0.4332. Okay? That's what it gives you. And then this is another example. Now this example, when you convert to the z, it's between minus 1 and 2. But you can break it down into two. Between minus 1 and 0, and then between 0 and 2. So between minus 1 and 0 is the same thing as between 0 and 1, which we got earlier as 0.3413. And now between 0 and 2, when you read from the table, it's under, so it means you read for 2.0 under 0, 0, it is 0.4772. When you sum it, it is 0.8185. Note that we are applying the OR rule, right? The addition rule here. So that is it. This is yet another example. So once you understand the basics, irrespective of how the question is twisted, you can always calculate the probability. So this one is to find the probability that the required equipment repair time is either less than 25 minutes or greater than for 75. So it's still the OR rule, so addition. So it's less than 25 or greater than 75. Because these are mutually exclusive, you add them, right? So that less than 25 is z counterpart is z less than minus 2.5. Greater than 75 is z counterpart is greater than 2.5. So you can find this one and find this one also and add, okay, and we've manipulated it. Now, by symmetry, okay, this and this are the same. So you can write this as twice the value of one of them. And then you get your probability value as 0.0124. So these are how they are calculated. Now, as I indicated, I've solved problems step by step to illustrate how you can calculate probabilities. And I think with this, it shouldn't be difficult for you to calculate the appropriate probabilities, irrespective of how the question is twisted. Now, this is where we bring part 1 of session 7. We will see you shortly for the part 2 of session 7. Thank you very much.